If you are in Seattle, it's a sort of beautiful day, February 8th. The sun looks like it's trying to come out. Welcome to the third session for the Commercial Heat Pump Water Heating Design and Maintenance Deep Dive. If you missed the first two sessions, they are up on our website. I think I have the most recent one up there. I'm missing the slideshows, but you can watch the videos. I'll get the slides up there soon. It looks like I'm experiencing degraded audio. Is everybody hearing me okay? Evan, can you hear me?
Yeah, I can hear you okay.
Okay, good. Okay. I just have an error message. Sorry, everyone. Thank you for joining the Lighting Design Lab powered by Seattle City Light this morning, where we've got DNR and Ecotope here to give you this third installment of this content. And with that, I will hand it over to Sarah.
Thanks, Katie. Good morning, everyone. My name is Sarah Pastor. I'm with DNR Learn, and I will be joined by Sean Hoffman today. We will both be your moderators. So if you ever have any questions throughout the presentation, unfortunately, you cannot unmute yourselves to ask them, but we encourage you to send as many questions to the little questions tab or the chat tab, and we will answer them during some dedicated question breaks that Evan has throughout the presentation. So please feel free to ask away. The presentation today will be around 2 hours with a break in between. And without further ado, Evan.
Hey, sorry about that. Can you see me all right?
Yep.
Yeah, sorry. I feel like I'm picking up a cold or something, so I might cut out every now and then to get a cough or a sneeze out. So I hope that's not too distracting. So today we're going to be talking about commercial heat pump water heating. And specifically, we're going to be talking about taking you from the engineer's design over through the details of the system. And so the background I have around this is I am an engineer at Ecotope, and so I work solely with commercial heat pump water heaters. And so I've also come from Colmac Water Heat, and so I interface with contractors and designers and installers to get these systems in. So the key questions we're going to answer today is how do I choose the right equipment, and what steps do I need to take to implement a commercial heat pump water heater system? So there's a lot of different equipment types that you can choose, and a lot of different locations that this equipment can go into. And so you need to be really in tune with what's available on the market and what kind of details you need to think about to implement this equipment. And so the steps we're going to walk through today is to kind of fill in the details of how to work with your manufacturer to determine some of those nuances that you need to be aware of as you're detailing this equipment out. And we're going to be using Slido today to answer a lot of questions and provide a lot of feedback from you all. So it's a really easy interface that you can use with a phone app or online. And what you're going to do is you can go to slido.com, or if you've used it before on your app, you can go to your Slido app, and then they'll prompt you to enter a code, and you can enter design 3 in that code. And then that will provide an interface for you to provide feedback on some of the questions I'm asking, and then in some cases give me a little more information about you so we can cater this to what you all want to learn today. So we're going to try this out with an introduction survey. And you see there's also a QR code in this corner. So a lot of times you can scan that code with the camera on your phone, and then you can go to that survey and answer it through your web browser on your phone that way as well. Or you can enter design 3. So at this point, I'll take a second and let you get onto Slido, and then you can go ahead and answer the questions, and I will answer some of these live and then get some feedback from you guys. So the first question is, what is your role in regards to commercial heat pump water heating systems? So my role at Ecotope, I'm a design engineer as well as a research engineer. So I'm involved in making designs around heat pump water heater systems, but also working with manufacturers to get the right information out there and figure out the parts of the systems that aren't quite as well known through lab testing or working with manufacturers or researching literature that's already out there. So we have a design engineer in the audience so far, so this should be really helpful for today. It's kind of tuned for design engineers and installers like plumbing contractors or mechanical or control subcontractors, but it's really good to see this information throughout all levels of the heat pump system design. And so there's an architect in the audience as well. That's really great because we'll cover some high-level concepts about heat pumps and their benefits on the building level. And so the next question is, what's your experience with heat pump water heater systems? And so we have a lot of novices, which is totally fine because there's a lot of novices in the field currently. So a lot of things I'll talk about today and in the next section next week will kind of cover all the things that even coming into it with no heat pump experience will be really important to know. And I'll cover a lot of high level as well. So it's not as mysterious, the entire process isn't quite as mysterious as it might have been.
Hey, Evan, if I can just butt in, we got one comment that design 3 at Slido is not working for someone. It's not working for me as well. I will reach out to someone who can fix this for us. In the meantime, the QR code was able to work on my phone. If you could switch over to your phone, but I will let you guys know when we get this all fixed up.
Okay, great. Thanks for letting me know that. Let me know if I need to reset anything or restart the slideshow to make those work, and we'll get it going. And muddy waters in this process is there are so many options. Yeah, I mentioned there's a lot of different ways that heat pump water heaters come to the market, but a lot of the things I'll talk about today are kind of general guidelines that you can apply to any type of option. So hopefully we can clear that up a little bit. And today we're going to look at a case study in Seattle, Washington called Jackson Apartments. So this has been a really successful heat pump water heater installation, and it's a market rate building. So it will show, we'll kind of refer back to this throughout the presentation as well and use this as an example for how we would go about this process in something like this multifamily building. So you can tell here's a picture of Jackson Apartments, a few different viewpoints. So we have the two buildings here on the left, and if you zoom in a little bit, you have this really beautiful corridor they call the mall that has, of course, this kind of brilliant architecture of the plants as well as the building itself and this structure here. And you can tell that the architect put a lot of thought into how to make this the best experience for the residents. A lot of native plants, so then as soon as they step outside, they kind of feel like they're in nature and just, overall really positive experience. So we want to make sure putting a heat pump water heater system into a building like this, it's not going to be acceptable to degrade their experience in any way. So they're not going to want to notice that there's heat pump water heater system because they have to shower between 10 and noon or shower in shifts or anything like that. So it needs to be seamless. And so zooming into the mechanical room of Jackson Apartments, here are some features of the overall system. So we have new construction, so we have a little bit more flexibility on the mechanical room dimensions. So we can design the heat pump water heater system and then somewhat work with the architect to say we need this much room in the mechanical room for a perfectly functioning system. And that system in this building consisted of two Colmax CXA15 heat pumps, which are single pass heat pumps, and they're paired with three 500-gallon primary storage tanks. There's also a parallel loop tank, which is heating the recirculation loop that circulates throughout the building, and it has a backup electric heater for redundancy, as well as this smaller CXV5 heat pump water heater that's keeping this separate tank warm. And we'll talk about why these are two separate systems to handle those jobs later today. And this is all located in the parking garage, and it's really important in this setting with this equipment that it is located in the parking garage, because it will provide warmer air to the heat pumps as that air passes through the parking garage and enters those heat pumps. And because we're using a heat pump water heater system, they were able to see about a 15% annual energy savings by utilizing this equipment. So here's a picture of the mechanical room from the parking garage. So we were just looking in the door in that last picture with the recirc heat pump on the outside and then all the main equipment in this cube here. And what's happening here is we have air that's going to, so I'll zoom out a little bit more in the fact that these heat pump water heaters, they need warm air to extract heat from that air to then put into the domestic hot water. So you need to make sure they have a consistent air supply, usually a pretty high volume flow, and it needs to be warm enough for that manufacturer's requirements. So what we're doing here by placing them in the garage is we're putting them on the bottom floor, and the air that gets sucked into those heat pump water heaters has to be drawn through 3 floors of this garage. And as it does that, it passes over this semi-warm cement, and the heat from the cement is actually transferring into the air and acting as a buffer. So even if you have a really cold night in Seattle, the overall garage temperature will be warmer because that cement has held on to the previous day's heat, as well as the heat from the earth, because it's 3 stories down into the ground. So the cement in the garage is never below 40 or 50 degrees. So by the time the air passes all the way through the garage and gets to the heat pumps, that air is going to be warmer than 40 degrees, which is the heat pump's minimum operating temperature in this situation. And then after the air passes through the heat pumps and that heat is extracted out of the air, it will continue out and then be sucked out of this garage exhaust that goes to the outdoors. So there's constantly fresh air circulating into the garage, warming up, being cooled down by the heat pumps as they extract that heat out, and then exhausted outside. And here's a picture of what's going on with the plumbing in this system. So we have, you can think of this as serving 2 different functions. The first is heating water up to the temperature that the occupants can use. And to do that, we have primary heat pump water heaters and primary storage that are receiving cold city supply water, and they're heating that up to about 140 degrees in a single pass, and the storage is storing a lot of that water. And then separately, since we have these long pipe runs in the building circulating throughout, we need to make sure the water inside those pipes doesn't cool down if the fixtures aren't being used. So in almost all large central systems, we have this circulating loop. So we'll supply hot water to the building, and then slightly cooler water will return back from that circulating loop to be reheated. And a lot of heat pumps don't like to heat warm water up to a high temperature. They like to heat really cool water. So you have to have a heat pump and storage that are dedicated for this job to know that we can handle that warm return water that's coming from this loop. So in this building, these 2 systems are operating in parallel, and they're both serving that mixing valve to make sure we have enough water circulating and keeping those pipes warm, as well as enough water to serve the actual fixtures when people need to wash their hands or take a shower or anything like that. So the key takeaway from this case study is improvements in energy efficiency do not have to come at the sacrifice of comfort. So even though we're installing a really energy efficient system, it doesn't mean that the occupants need to change their habits or even notice that the hot water supply is any different at all. So it's totally no different to the residents, but we're saving a lot of energy by installing this different equipment. So I'll leave a pause for questions there. So go ahead and scan that QR code and we can open the survey. Whoops. And Sarah, are you still able to get into this question using that QR code?
Yeah, the QR code is still working for me. I'm still figuring out what the Slido code issue is.
Okay, great. Yeah, and if anyone doesn't want to use Slido, you can always drop questions into the chat, or there might be a Q&A section as well. And then I'll have Sarah or Sean bring those questions up, and then we can answer in these sections, or she can feel free to stop me throughout the presentation and address those questions if they're what I'm talking about at the time and it makes sense to do so. So I'll go ahead and move on from here. Yeah, if you didn't have time to enter your questions, just put in the chat and we can answer those there. So what we'll be talking about today is the transition from receiving an engineer's design as an installer and turning that into a system that is fully operable. So first off, that is maybe finding your contractors or subcontractors, and we'll talk about the attributes that are important to look for in a subcontractor working on a system like this. And then we'll talk about detailing your equipment and some of the little fine details that might vary between equipment manufacturers, as well as vary between projects that you'll want to communicate with your rep about. And then the verification and purchase process to make sure you don't leave anything behind that you actually need for a certain project. And then lastly, we'll talk about the installation and startup of this equipment at a really high level and what you need to keep in the back of your head while you do that. So step one is finding your subcontractors. So this can apply on many different levels, whether it's a GC looking for a plumbing contractor, or them looking for a subcontractor to handle controls on this equipment. But this applies in general on all sorts of levels. So it is important to gauge the experience of your subcontractors regarding heat pump water heaters, but I would say it's not crucial that you find someone that has installed the heat pump water heater, just because there's a lot of great contractors out there that just haven't really had the chance to install this equipment yet. So more so than the experience specifically installing a heat pump, you'll want to make sure that the attribute you see in a contractor is the ability to communicate and learn new things, and the optimism in installing this new technology. Some contractors want to push really hard to just change it to a boiler system that they're super comfortable with, but there's a lot of great options for new technologies out there, as long as the installer is willing and able to learn about those technologies and ask questions whenever whenever any blind spots come up. And that leads and is kind of in parallel with the importance of open communication throughout the entire project. Right, so there's a lot of back and forth in a successful heat pump water heater installation. No one's ever going to know absolutely everything that needs to go into this installation, just because there's no really set in stone standard practice for these yet, and the equipment is always evolving, so there's going to be little fine details that might change that you need to keep up to date with. So part of this communication and the value of this communication is getting educated on these systems. So at a high level, you need to make sure you understand the overall concept of how heat pump water heaters work, and there's different channels to go about that. One is through DNR Learn, as they've helped with this presentation today. They have a lot of resources and modules that you can look into and that give general information about heat pump water heaters. And then on a project level, you'll need to make sure that you understand the engineer's reasoning behind why they've made the design the way they have, because you might be really familiar with boiler systems, but heat pump water heater systems are a lot different, and a lot of times there's good reason behind piping that would seem wrong in a lot of other cases. So having a call with the engineer to go over the design and making sure they answer any questions you have about it is really important. And if that engineer is not able to answer questions based off what you have on the design, it's really great to get a rep, a manufacturer's rep, or maybe even a manufacturer's applications engineer involved in this process. Because a lot of times the engineer is relying heavily on the rep or manufacturer to implement that design. So it's good to have basically get all these facts from the source in conjunction and cooperation with the engineer. And on a manufacturer level, there's always a lot of webinars or design materials available from the manufacturer or their rep. So it's worth the extra time really investing in a certain manufacturer's information before the installation process or the detailing process starts, so you have a good baseline level of knowledge you're working off of. And at that point, you can start kind of getting a gut check when you look over designs and sort of know what questions to ask the manufacturers or reps as you fill in some of the details that the original design might not have. So after you've learned a little more about heat pump water heaters and communicated the design intent with the engineer, your next step is going to move on to equipment selection. So there's usually several manufacturers that might fit the design intent, and typically you'll see one manufacturer as the basis of design on this schedule. But you need to ask yourself, what about this equipment makes it fit this design that other pieces of equipment might not, right? There's different refrigerants and different envelopes for this heat pump equipment. So sometimes that one manufacturer is the best option for this design, but other times you might have to go with different manufacturers based off lead times or some other factors we'll talk about. So some main considerations for the equipment you're looking into and how you're going to match it to the schedule that you've received from the engineer. Or as an engineer creating a schedule, you want to look at the design conformity and how well the heat pump fits into the design, as I mentioned, as well as the lead time for these heat pumps and how that aligns with the project. There's a really wide variance in the lead times on these heat pumps right now, especially with a pairing of the lead time issues for a lot of the components they have to use, as well as the really quickly peaking interest in heat pump water heaters based off their really high efficiency. So you want to check with the manufacturer, their rep, on the lead time of this equipment and how that fits into your project. And sometimes the gestation period of these jobs is really long. So sometimes even the model that is on the schedule might not even be available from the manufacturer anymore. So like if you have an example with Colmac is they sold the HPA15 for a really long time, but they have now transitioned over to the CXA series. So there was a time where a lot of HPAs were on these schedules, but you couldn't actually buy that equipment. So you had to talk to the rep and determine how to best fit in a CXA to this design and what details you need to consider as this product has changed. And one tip I would have for equipment selection is support from a manufacturer is more important than a lower price on a heat pump. And I say that because there's always little details that you're going to need to go over and adjust in your project, whether it's during installation or even during the design phase. And if the manufacturer or their rep isn't available to answer questions you might have during that process, that could lead to either mistakes in installation or really long delays in the design or installation process that will end up costing you more money in the long run by dragging some of these items out when it could be a really simple answer from an experienced rep or manufacturer. And I want to pause here and ask what your experience is with these first steps. And so we have, whether you're a pro or this isn't even valid, and you can go ahead and drop in the chat any extra tips or any pain points you've found in this, and we might be able to address that. So we have some that.
Sorry, Evan, we do have one question that just came in. Were the Colmac units you were showing ducted to another location for the air intake?
They had open air intake and their exhaust was ducted, and this is pretty common. So then the air will flow freely to the inlet of the heat pump through the garage, all the way through the garage, just sucking in from the mechanical room. And then the outlet is ducted to a different location. So it causes that natural circulation of air to the inlet, and there's no extra pressure drop or ducting you have to worry about. Then the outlet gets rid of that cold air so it doesn't recirculate into the room.
Great, thanks, Evan.
So we have a few that will take these steps soon, so hopefully this will help. And then we have a pro, at least one pro in the audience too, so hopefully I'm providing some value there, and I'd love to hear some feedback based off what I'm talking about and what you've experienced so far. Yeah, and any more questions or feedback, just drop that in the chat as I go through here. In terms of equipment selection, there are a few main things you'll need to think about and a kind of a desired order that is good to go through here. And so the first thing you'll want to choose when you're picking a specific piece of equipment and detailing it out is the heat pump and the storage tank. And these are grouped together because they rely heavily on each other when it comes to tank connection locations and controls points and things like that. So even to the point where a few heat pump manufacturers now actually produce their own tank lines to pair with their specific heat pumps. So if that's an option from the manufacturer you're choosing, then I would definitely recommend that you just put that tank that the manufacturer has designed for that heat pump operation in paired with that. And so the available products when you're looking at a heat pump water heater, these are really quickly evolving. So I would not reference this slide in a year or something like that when you're going to choose a heat pump, but this is mainly what's on the market today. So first of all, we have these multi-pass integrated residential or small commercial heat pumps, and these are package systems with the heat pump and the tank all together in one package. And you'll see these more commonly in small residential settings or distributed systems where maybe you'll have these heat pumps in the closets that serve a couple of units in a building rather than a bunch paired together in a large central system that serves that loop like we saw at Jackson. And then we have the single pass heat pumps that primarily the CO2 single pass heat pumps are the ones that only operate in single pass, so that's why they have their category here. And we have Sanco 2 and Mitsubishi on the market here, and what's great about these CO2 heat pumps is they have a low GWP, which I'll talk a little bit more about later, and they can go down to really cool temperatures. And these are both outdoor rated, so a lot of times you'll just see these put right on the roof and circulating that outdoor air directly. And then we have the R134a Commercial units that can typically operate in single pass or multi-pass because of their refrigerant limitations. And the biggest limit on this category here is they cannot withstand cold temperatures, just like the R134a residential units. So they bottom out at about 40 degrees. So that's why we saw that Colmac heat pump placed in that garage as a buffer space, so then it didn't see temperatures below 40 degrees. So if you're in Hawaii, you might be able to put this out on the roof, or somewhere in the south where it doesn't get below 40 degrees throughout the year. These can be placed outside just fine. But if you're in places like Seattle where you see quite a few days below 40, then you'd need to place it in a buffer space like a garage or provide redundant backup for those days where it drops below their acceptable temperature. So here's a visual of the temperature range of what these refrigerants can handle. And we have the kind of the top three most common, I'd say conventional refrigerants on this chart, but there are a lot of upcoming lower GWP refrigerants available. A couple that come to mind are R513a to replace this 134a and R454b I've seen as a replacement for this 410A, but those are going to continue to evolve, and I don't think there's anything that the market has completely settled into as a replacement for these more conventional refrigerants that have the higher GWPs. So in terms of temperature, you can see that the CO2 refrigerant can go really low in temperature as well as the R410A. So if you're looking at an outdoor installation, you're trying to pick a piece of equipment for that, then the CO2 or 410A might be your best option. While the buffer space installations like the garage would be the R134A option, or at least that would be one great option for that. In terms of GWP, there are municipalities that are cracking down on the GWP limitations. So you'll want to consider that. And when I say GWP, I'm talking about the global warming potential, which is basically the ability for a gas to trap heat in the atmosphere if it was released. So the baseline for this metric is CO2. So if you release a pound of CO2 into the atmosphere, it's going to hold that heat in through the greenhouse effect. But if you were to release a pound of R134a refrigerant into the atmosphere, that would be like releasing about 1,400 pounds of CO2 in terms of the amount of heat that it would hold into the atmosphere. And same with 410A is even worse. 1 pound of 410A would be like releasing 2,000 pounds of CO2. So one equipment leak, if it has 5 pounds of refrigerant in it, and that refrigerant leaks out of one piece of equipment, that's like releasing over 10,000 pounds of CO2. So that's why there's a push to to transition to these lower GWP refrigerants. Another consideration when you're looking into refrigerants and heat pump performance as a whole is the effective air temperature on the heat pump performance. So since we're trying to pull heat out of the air, it does that a lot more easily if the air is a lot warmer, right? The heat pump has to work a lot less hard if it's pulling heat out of 80-degree air than out of 10-degree air. So when you're designing these systems or you see it on a schedule, you want to make sure that the performance that you're looking at for this heat pump is tied to the lowest design temperature that your project will see. So on the left here, we can see at, we'll say 45 degrees, you're seeing about 170,000 BTUs out of this equipment. But a lot of sales flyers might post the performance at 70 degrees, so you're around 250,000 BTUs. So if you size your project based around this nominal capacity that you might see on a sales flyer, your project will most likely be undersized. And you also have to consider the entering water temperature that these heat pumps will see. So here's a CO2 performance graph, and what you're seeing here with these three different lines are three different entering water temperatures that the heat pump will see. So if you're in a design where you see consistently high entering water temperatures, maybe it's being preheated by some sort of process, you really need to take that into consideration when it comes to how many BTUs you're relying on out of this equipment. The CO2 unit, for example, it peaks at about 75,000 BTUs if it sees 120-degree entering water, where if you had cold city water coming in at 45 degrees, your design here at 60-degree air would be 195,000 BTUs. So that's around 2.5 times the capacity if you have cold entering water. So that's not the same for every manufacturer, every refrigerant, but something you need to keep in mind and a question you need to ask as you're detailing these systems out. So thinking a little bit more about storage tanks, we talked about how it's really important how they're paired with these heat pump water heater systems, and it's really important how they're plumbed up. So we need to think critically about the storage we're selecting. And from a high level, it's okay to see a lot higher volume of storage, and actually preferred to see a lot higher volume of storage in a heat pump water heater system than you would with the equivalent boiler system, because these heat pump water heaters have a lower recovery on average, so they rely on the storage to cover the peak loads from the building. Like if everyone was to get in the shower at the same time in the morning, the storage would supply most of the hot water while the heat pump trickle charges the storage throughout the day. And these are probably the top 3 ways, or the 3 most common ways I've seen storage piped up in the field. And I would definitely say that the third way here is my preferred. And I'll explain why here, but I'll start with I'll just go from left to right here. So the common theme is that we have stratified storage. So we have hot water in the top of the storage tank and then cool water in the bottom of the storage tank. And those are separated really thoughtfully because it allows the heat pump to suck in that really cold water that makes it run efficiently, and it provides a greater storage capacity. So on the left here, you would think to provide the greatest storage capacity, we'll just this is the heat pump supply and return. We'll bring the heat pump supply water, hot water, and dump it straight into that pipe that goes into the top of the heat pump. The heat pump on average supplies 140-degree water. So in theory, that would give us the most capacity out of this tank, while the cold water is pulled directly from the bottom of the tank to be heated up. But the downside to this is at the beginning of your run cycle of your heat pump, all this water in the supply pipe will have cooled down because it's just sitting there waiting to be heated. Sorry about that. So as soon as the heat pump starts, this cold slug of water will go straight to your supply line, which will then go out to your mixing valve and send your mixing valve cold water. So you'll have a slug of cold water there, and any variations in your heat pump leaving water temperature, which it's going to vary slightly as the heat pump warms up and as things change. Any of those variations are seen directly by the mixing valve, and the mixing valve has to respond to that really quickly. So to mitigate that, we can decouple this line and provide a separate connection in the top of the tank. So if the heat pump is supplying water to the top of the tank rather than directly to this supply line, there's that buffer. It will mix in with the rest of the water before it's supplied to the mixing valve. So you have a much more constant water temperature supplied to this mixing valve. So the second thing I've seen here is utilizing more typical connection locations on a standard tank and supplying this hot water from the heat pump right to the middle of the tank. And that will work in most cases when the tank's fully charged, because our goal, remember, is to have hot water on the top and cold water on the bottom, like we see here. So if this tank is fully charged with hot water, we're dumping this hot water into the hot water portion of this tank, so we're good there. But as soon as this tank starts to draw down and hot water is being sent out to the building, this cold water will backfill up into the bottom. And as soon as this cold water reaches that inlet from the heat pump, the cold and hot water will mix and make this warm water that may be cooler than what the occupants can handle or what is acceptable for them. So the best option, in my opinion, is going to be this configuration here, where we have dedicated supply and return lines from the heat pump, but that supply line is located way up top in the tank. So now it's dumping this hot water in the top of the tank. There's still separation from that supply line, and then the cold water is being pulled out of the bottom of the tank. So we have really high tank capacity, we have really good stratification, but we also have that separation between the heat pump, the cold water line, and the supply line to the building. So definitely feel free to ask any questions in the chat, because I just threw a lot at you in that slide, and I'll move on from there. But I can back up here if any questions come up down the road. So to see this in practice, we've simplified the system a little bit, and I just told you that there should be this separation from the heat pump and the mixing valve in practice. But this is an old animation, and it really illustrates how the stratified storage works when you're bringing really cold water in from either the city or from the bottom of the tank and heating it up to 140 degrees. So right now we have a cold system, just like it would be if you would have just plumbed it in and are about to start the heat pump. And then we'll start the heat pump up for the initial fill as it pushes hot water into the top of this tank and then works its way to the next tank. And so what happened here is we have stratified storage. So it's charging the tank from the top, and you can picture these two tanks as one tall tank because you have the top of the first tank connected to the bottom of the second tank. So if you were to stack the second tank up on top of the first tank, you would have that hot water charging the top of the tank, then the cold water coming in the bottom of the tank. And then after the heat pumps filled this system initially, we will have a hot water draw from the building, and then that cold water will make its way up into the bottom of this first tank in series. So, and at this point, the heat pump hasn't turned on yet because this cold water hasn't made it to the heat pump sensor. So this sensor location is really important to think about in terms of how your control sequence will operate. We'll talk more about that later. But at a high level, as soon as all this cold water fills the bottom of the tank and the cold water reaches this sensor, that's when the heat pump will turn on and either try to supply the building with hot water or recharge the storage. In this situation, you saw the storage continue to get cold, and that's because everyone has turned their showers on at the same time, and the storage is providing more hot water than the heat pump can make up. so that storage continues to go cold. And then as these showers, as people are done showering or stop using as much hot water, now the heat pump's supplying more water than the building requires, and it can recharge that storage. And then once the storage is totally recharged, the heat pump sees that warm water coming back, meaning that hot water's made it all the way to the bottom of the tank, and now it's going to shut off and know that the load is satisfied. So applying this to our system at Jackson Apartments, here are all of these tanks plumbed in series, one after another. So you see the cold water coming into the bottom of this tank on the left, and then the hot water coming from the heat pump is going to be entering the top of the tank on the right. And then from there, it's going to go out to the mixing valve and go satisfy the building. So we see this plumbing, we see the top of the first tank go down to the bottom of the next tank, and so forth to the third tank. So you can picture these as 3 tanks stacked on top of each other because they're connected top to bottom and offering this one really tall stratified tank. And then here we see water heater 3 as it's labeled. This is our temperature maintenance heater that is heating that recirculation loop. And then just out of the screen here is that heat pump that's paired with this heater. So it's serving that mixing valve in parallel. So then that loop can continue to circulate and return back to this tank. And then these tanks remain stratified with that really cold city water coming in the bottom rather than the warm water that would affect those heat pumps differently and potentially mix this storage up. Okay, here I think I'm going to take a pause and let you absorb all of what I've talked about, and we might take a 5-minute break to write down any questions or anything like that and put them in the chat, and then we can address those once we get back from this break. But I'll let you take a break to get water or coffee or anything else before we dive back in. So it's 10:47 right now. Maybe we can we'll aim for 10:53 to come back. All right, I'll see you then. Okay, we'll give it one more minute and then I'll dive back in. Okay, now that you have your coffee refill, you can wrap around some of these ideas, wrap your head around some of these ideas, and don't forget to drop questions in the chat whenever we're ready, and then we can dive back in. So after we've considered the heat pump and the storage, the next thing we want to look into are the controls options. And these are heavily driven by the heat pump and the storage tank based off connections and control locations and overall piping configuration. So it's really important to keep the heat pump and storage and how that's plumbed in mind while you pick out the controls. And our main purpose for these controls are to allow them to fulfill the design intent through the set points and the sequence of operation that the designer has laid out on the schematics. And later on, I will go a lot more deeply into the different controls options that are out there. So once you've picked the heat pump and the storage and the controls, the last thing is going to be the mixing valve, which is more driven by the design intent and what you're looking for out of the system, and less of a driver of how you will pick your heat pump and your storage or your controls. So that's why we kind of pick this last in this order of the three high-level components. And just because we're picking it last doesn't mean it's not a really important part of the system. So some considerations you'll want to make when detailing out a mixing valve is you'll want to consider the minimum and maximum water flows to the building. If the flow is too high through this mixing valve, it's going to cause a pressure drop that might make the pressure too low at the fixtures based off the design. But if the water flow is too low through a certain mixing valve, then it's not going to be able to target a temperature consistently. So, excuse me. So you'll want to make sure that your minimum flow rate on your mixing valve is a little bit lower, or your minimum allowable flow rate in the mixing valve you choose is a little bit lower than whatever your recirculation rate is on that circ pump, to make sure that you're always able to target a specific temperature. And the other thing that might drive your choice of mixing valve is the depth of controls your design has in the control strategy. So do you want to monitor specific temperatures coming out of the mixing valve and send an alarm if that water temperature is too low? Then an electronic mixing valve might be a good choice, because a lot of times those sensors are built in, but the mixing valve rep and the controls contractor will have to work closely to make sure that those can integrate well. And the level of water temperature precision is another factor that you'll need to think about if you're doing any sort of processing that relies on really tight temperature allowances. because these electronic mixing valves have a greater ability to nail down a specific temperature and stick to that, independent of what is being fed. And then the last thing that you'll select in detail as an installer will probably be these additional valves that you can get right off the shelf. And I say that with the caveat that there are supply chain issues, so as an installer, you'll know which of these components might be more difficult and that need to be ordered ahead of time. But these aren't dependent on the heat pump design itself. They're what you as an installer might be more comfortable with buying and selecting on a day-by-day basis. So I want to pause here and ask what your key takeaway so far is from the detailing and selection of this equipment. Yeah, lots of storage is good in these systems, right? We want to provide plenty of hot water for those peaks, but we want to also give the heat pumps enough room to run, to have nice long run times. And Sarah, were there any questions in the chat by chance as we wait for Slido to fill in a little?
Yeah, we're still not seeing any, or we're not seeing any questions in the chat right now.
Okay, great. This is a good question though. Is Legionella growth ever a concern in swing tanks with the top fill? So swing tanks do vary in temperature, and I think something that helps prevent Legionella growth in the swing tank is the fact that there's constant flow and constant mixing in this tank, so there's not stagnant water at times of no usage. If you're in a system where your recirc pump shuts off for a significant period of time, that's when you need to start reconsidering whether you use the swing tank approach or something else where you're storing at a much higher temperature. But in terms of the top fill, I'm not totally sure if I'm interpreting what you're asking correctly, but the top fill of how we were talking about the storage connections between the heat pump and storage is a little bit different than the swing tank setup, because the swing tank, we're aiming to mix all this water up and provide a more consistent temperature as the hot water from the primary storage fills into that and essentially heats it up as it mixes in. Jackson uses parallel temperature maintenance, so they're actually heating that temperature maintenance tank up to 140 with the heat pump water heater, rather than relying on that swing in temperature to provide a buffer as the usage from the primary storage comes in and heats that up from a cooler temperature. So I hope that answered your question. Definitely send some follow-up in the chat or even in here, and if you want any further detail on that.
Hey Evan, we actually got a question. What temp do you deliver the water at? And say you have 3 storage tanks, what temp would you send the temperature sensor at? That's from Jack.
Yeah, so yeah, great question. Usually it depends on the manufacturer again, like Co2, for example, and I think even Mitsubishi, they like a higher storage temperature. Co2 specifically 149. So that's what we would set this, that's what we would set the temperature to that we deliver to the storage. In terms of the controls temperature, that's a little different because we're talking about that stratified storage where you see a significant drop in temperature as soon as that cool water works its way up to the temperature sensor. So even though the storage will sit at 150, we might turn the heat pump on when that temperature sensor drops down to, say, 120. So there's a really strong buffer there to make sure that that cold water has actually made it up to that temperature sensor. So that's a great point though to bring up. And if you're seeing a control sequence and you're seeing the heat pumps turning on at 120 or maybe even 100 degrees, that doesn't mean that the water temperature above that sensor is going to be 120 degrees when it turns on. That just means that the tank has filled with cool water up to the point of that sensor location before it turns on. So yeah, great question. And sorry, was there a second part of that question that I might not have addressed? Oh, the delivery temperature. Sorry, usually we'll see between 100 and 125 in delivery to the building. And that will sort of depend on the length of the loop and a few other factors, but I've seen 125 pretty typically there.
And then we have a like follow-up comment to that from Jack. If you're using city water with chlorine treatment, you are unlikely to have Legionella concerns. Right.
Yeah, so that is an advantage there with the chlorine treatment, or sometimes engineers will even, I've seen engineers want to avoid mixing valves based off previous experience and actually use UV, I don't know if you call it filtration, but UV water treatment to get rid of that Legionella risk as well. So there are alternates to bringing it up to that higher storage temperature, but additional considerations with each of those alternates for sure.
Thank you for that question. Keep them coming.
Yeah, definitely. I love answering questions, no matter how far left field they seem. And these were all super relevant, but just in general, I love answering questions. So the last step step 4 we'll talk about here is it's kind of a bundle of controls, conversations, and considerations. And the reason we have these together is when I picture a control schematic or a controls design, it's kind of the material representation of the coordination that's required throughout the entire system, because a lot of times the control system in a domestic hot water system will touch a lot of different components. And so those components need to interact really closely with each other to satisfy the design intent. And so the conversations that all of these different trades will have are exactly the same way. Like you might have a trade hooking up a ducting system to the heat pumps, while another trade hooks up the electronics, and then another trade hooks up the low voltage controls, and they all need to be able to coordinate to have an effective and smooth project installation. So the first mention in that is controls, and that they are super important. I did a lot of startups at Colmac, and there were quite a few projects where there wasn't even a temperature sensor in the tank, and no one had actually considered controls. So the heat pump was just sitting there, powered off, nice and happy, because it had no clue what was going on in the storage tank. So there was nothing telling it that it actually needed to run and heat water. So super important to work with your rep and your engineer to make sure that these controls are telling the heat pump the right thing, and that they're monitoring the right sensor locations and the right values to be able to make the right logic happen to run this heat pump. So it's really important to define controls commitments as you're talking about this project. Like what's the plumber going to be responsible for, and what's the actual controls contractor going to be responsible for? And that interface is really important, because a lot of times, even if the contractor is landing the sensors, then those sensors still need to fit into the thermal wells in the tanks that the plumber will be installing. So that interface is really good to have coordination between the rep or manufacturer, the controls contractor, and the plumber, and sometimes even the mechanical, to make sure you know where those lines in the sand are and that those 2 points are going to interface seamlessly. And your end goal here will be to, of course, to make sure that the equipment will start up correctly. So a good question to ask yourself is, based on your understanding of these controls and how the heat pump works, all the communication you've had so far, would this equipment be able to satisfy the design sequence of operation if a factory technician was to plug in set points that this control system is set up for? Like, if there's 8 steps in the sequence, are there baseline set points that can be plugged in by this tech, and it will actually go through all 8 of those points? Oftentimes, the sequence can be a little more general, or it will be a little more general coming from a designer that will kind of incorporate the overall sense of what the design and the project is looking for, but will not address the specific piece of equipment's set points and how it operates internally. So a lot of times that will need to be tweaked in collaboration with the rep and the contractor and the engineer to make sure everyone's on the same page and the original design intent is still seen, but now it's actually being applied to this specific piece of equipment in this project. When we talk about controls, there are a few different ways to go about it, and there's different levels of controls that have different advantages and disadvantages. So the first level is going to be the internal interface, where the heat pump itself, the heat pump's onboard controls tell it exactly what to do. So usually that will mean there's a computer on the heat pump and it runs its own sensors out to the tanks, and it will react based off the tank temperatures. Where there's also an option where the heat pump runs itself mainly, but it also reports to an external system like a BMS that's already installed in the building and is sending values to the maintenance crew. While the external interface means an external controller that is not a part of the heat pump water heater itself is telling the heat pump and other components in the system exactly what to do. So a little more detail on the internal controls interface. Like I mentioned, the heat pumps control themselves completely, which the advantage there is the heat pump manufacturer knows more than anyone else on what these heat pumps can handle. And often so that means the sequence that is most ideal for these heat pumps is best known by the manufacturer. So if that's built into the heat pump itself, the heat pump's going to know what conditions it wants to target and what sequence will best satisfy those conditions. The downside to that is in this system, the rest of the system is blind to what the heat pump's doing. So if you're looking at remote troubleshooting or you want any kind of feedback from your system, then that's going to be harder to get here because all the controls and logic are just on board of the heat pump and usually not very transparent. The sequence itself is not very transparent if you're just looking at the heat pump. The advantage here is, another advantage here is it's oftentimes going to be a lot cheaper control sequence overall if you just use the heat pump's built-in logic, because now you don't need an external controls contractor aside from maybe pulling some sensor wire to the tanks. You don't need a custom program that could potentially not operate within the bounds of what your heat pump will most ideally operate with. And then this internal interface, the temperature maintenance system, will often run independently, blind to what the heat pump's doing, because they serve 2 different duties, so there's not really any use in the heat pump telling the the primary heat pump telling the temperature maintenance heater what to do. So they're kind of on 2 different islands in their control sequence and logic. So the heat pump BMS interface I've seen done really successfully, and it has all of the features of the internal heat pump interface, but now you can actually monitor the system through external eyes and see what's going on. So here we have a picture of a heat pump with its onboard controller, but now we also have a schematic of the entire system and all the temperatures within that system and the status of whether these heat pumps are running or not to satisfy that. So the heat pumps will have their own controls that say, this tank is cold, I'm going to turn on, and I'm going to run for this long until I see X temperature. But the BMS is available to kind of provide transparency into that and send out alarms if, say, a threshold temperature is met where too many tanks are cold. Let's send an alarm out before we start getting hot water complaints, so then someone can address this problem. And then the last option here is the external interface, where a third-party controller is handling all the logic in this control system, and the heat pump is basically blindly running whenever the controller tells it to. And this can be really successful, but it can also run your heat pump in a way that is not efficient or can be harmful for your heat pump if this external controller is not set up correctly. So it's super important if you are using this external controller to make sure that that contractor is working really closely with the engineer and the manufacturer or their rep to make sure that the controls jive with how the manufacturer wants this heat pump to be ran to make it reliable and efficient. A big advantage of these external controllers is they can both provide transparency into the system, and they can provide a really flexible control system in case your domestic hot water system is tied into other systems that it relies upon, or if there's auxiliary heating or anything above and beyond the kind of basic heat pump system that the manufacturer has designed their heat pump to work and be a part of. So an overview of these tiers, we talked about the internal interface where the heat pump handles all the controls and logic, the heat pump / BMS interface where you have a little bit more transparency from that external BMS, and then the external interface where the third-party controller is blindly telling the heat pump, or the heat pump is blindly listening to the third-party controller that is monitoring all the tanks and providing a more flexible control sequence based off what you need in a more complex system. So as it refers to Jackson, they are actually using an external controller because we have redundant backup systems. This is one of the first CXA installations, so the building management is more comfortable having redundant electric heating that is in parallel with these heat pumps in case the system gets too cold or falls behind. So we used an external controller because Colmac's internal controls at the time didn't offer that electric backup as part of their control sequence. So the flexibility that the external controller offered was attractive in that way. And it was actually, this works really well in Seattle with Colmac's rep because the representative that sold the controls also sold the heat pumps, so they were really in tune with how well these heat pumps work. They had been selling them for over a decade, so they were really in tune with the sequence that works really well for these heat pumps, paired with how the design functioned and the piping logic and all of that. So they paired together really seamlessly because of that rep's knowledge and working closely with the manufacturer and with Ecotope to carry that out. So I'll take a pause for questions here. So go ahead and scan that QR code and bring in any questions about the control sequence or coordination throughout the installation process.
We do have a question in the chat if we want to hit on that while folks are getting their questions into the Slido.
Yeah.
The question is, it's a follow-up from the previous question that Sean asked you, Evan. On a multi-tank system, if the temp sensor is set at 120 or 130, would you ever really need to use a temperature maintenance?
Yeah, you would, because if no matter what your primary storage temperature is, if you don't have usage out of the building, then you have this circulating water that would cool down, right? So even if you had 150-degree water and all these storage tanks ready to be used by the building, but no one opens a tap, all that water in the pipes that leading up to those taps would cool down, and then someone would have to run all of that water out of the pipes before the hot water from these tanks reaches that. So the temperature maintenance system we're talking about here maintains that water temperature, and it works in a way with equipment that can handle that water that has slightly cooled as it consistently circulates and keeps those pipes warm that leads up to those taps. And so, yeah, so it really depends on how much usage is in the building. If you had some application with consistent usage, that's when the temperature maintenance system isn't as necessary. But that's in a multifamily or residential situation, there's kind of always those times with low or no usage that water would cool down. Oh, this is a good question too. If I didn't answer that first question, definitely send some follow-up in the chat and I'd be happy to talk about it. But this next question is talking about any tips on integrating demand response with controllers. Is it easier with the third-party controllers? Yeah, so demand response, in the commercial side, it's still very quickly evolving on how demand response will work based on what the utilities really value and how systems are expected to respond to that. So I would say there's going to be definitely some really heavy coordination required between the manufacturer and the controls contractor that will be carrying out the sequence for this demand response controller. Tips on integrating those is, yeah, just make sure the primary focus on this still needs to be that the heat pumps are operating in conditions that will make them reliable. Because if you prioritize demand response so much so that the heat pumps are going to break down, then your overall water system isn't going to be robust enough for the demand response to catch on. And the main goal for the maintenance person or whoever is responsible for making sure that the tenants get hot water is that you always have hot water in the system, and you need the heat pumps to be able to operate reliably to do so. So I see a lot of really cool demand response in the near future, though, and a lot of really great opportunities to do that. So I'm excited to see what controllers come out and what sequences start to become a little more normalized to work with these heat pump water heaters. All right, so we can drop any more questions in the chat, and then I can move on from there. So after we've detailed all the control sequences and decided how our control is going to interface with our heat pumps, as well as selected all the equipment we want in our system, now it's time for the part that everyone loves the most, which is the submittal sign-off. So there's often some back and forth, especially if there's alternate equipment proposed based off of either local availability or lead times or anything like that. But it's worth doing your due diligence through the submittal process to make sure that it moves seamlessly downstream of this. So here's an example of some submittals that provided by Colmac at 23rd and Jackson, and some of the things that you'll need to check as you're requesting or submitting submittals through this process. So here we have a performance sheet of the CXA 25, which is in the larger building. And So, and we have the schedule below showing a heat capacity at 47 degrees. We have the model number, and we also have the voltage and phase and some electrical info, the FLA and MCA. And as part of the submittal package, you want to make sure that all those numbers still line up with the original schedule before you send the submittals out. This could eliminate a lot of back and forth here, and make sure that the heat pump you're using and any updated information from the manufacturer still aligns with what the engineer intended as part of that design. And so the other thing I didn't mention is the COP is really important on these heat pumps as well, whether it's to really just to provide the energy savings building owners looking for, or to satisfy any sorts of incentives. So you'll want to make sure that you have the most up-to-date information on the performance, electrical, and the efficiency of these heat pumps. So when they're actually installed in the field, you won't have any surprises. And so after the submittal is complete and you've received the sign-off from the engineer, now pretty shortly after that down the line, you can verify and purchase your equipment. So a lot of times you'll use the submittals directly to provide that information to your rep. And you want to make sure that you have any additional little details covered in that verification and purchase process. So when you're talking to your rep, hopefully at this point, you're really well connected with the sales rep, and you've gotten a lot of information from them on filling in the details of this heat pump design, as well as getting submittal data to ensure that everything still matches up with the original design that may have been created a while back now. And there are different levels of how tuned in these reps are to the latest equipment that manufacturers will supply, because you have to keep in mind that these reps have sometimes dozens of line cards. And so a really good quote that I've heard from a rep before is they know their knowledge on these projects it's an inch deep and a mile wide. So they have a really great understanding of a lot of different products. But when you're really diving deep into the details of a specific product, it's great to get that rep and the applications engineer from the manufacturer on the phone if it's a product you've never used before. So that's a really powerful way to make sure that you're getting all the details that that specific manufacturer requires, and that all of the information of your project makes it through to that manufacturer so they can fill any of these things in that isn't totally clearly listed on their documentation in a way that the rep can pull it out and drop it on a purchase order. So the documentation that is really helpful to share with the rep and this manufacturer as part of this coordination is going to be the sequence of operation, the plumbing schematics, equipment schedule, control schematics, and the submittal documents you've already created. And a lot of this should be shared during the submittal process as well, earlier on. And this can kind of serve as a final check in case anything pops up on any of these documents that the manufacturer says, wait, this actually wouldn't work with this piece of equipment. We need to make this little tweak before you purchase it, like adding a communications card, for example, or a cold weather package, or something that is really easy to change now, but once that equipment lands in the field, it's going to be a pretty significant update to have to change that later. So in terms of purchasing the equipment, you'll submit a purchase order to this rep, and you want to make sure that that purchase order specifically states all of those little details that need to be changed, and we're likely on the submittal. So the example here is going to be the compressor VFD, and those are important. We use those to serve a couple of ways. So we can turn that VFD down in really warm temperatures to lengthen the runtime of these heat pumps and make them operate more efficiently. And the VFD in this case also ramps up the compressor a lot more slowly when the heat pump starts and is a lot easier on the compressor. So that was something that has to be included in the PO on a separate line to make sure that that rep communicates that to the manufacturer. All right, so those that are pro in this process or have gone through it a few times, I want to hear some words of advice that you might offer to professionals that aren't as experienced in this process. At the same time, if there's any questions, Sarah, this would be a great time to address those.
Yeah, we don't have any questions yet, but folks can get those in.
Okay. Okay, I will hold on to this slide for a little while. I know it takes a little while to type all that in sometimes. Okay, we'll go ahead and move on, but if there's anything that you didn't get a chance to put in the Slido, put that in the chat and it'd be great to bring that up.
Someone came in with take a training course from Evan.
Oh, great. Yeah, anytime. Okay, so now that we have purchased the equipment, it's time to move on to the installation. So this is really where the rubber meets the road, and this is where it never fails that there are a few details that weren't caught throughout the design process or totally covered in the drawings. So it's still super important to maintain an open dialogue with the manufacturer's rep and the engineer during the installation, because these heat pump water heater systems are new and constantly evolving. So we want to make sure that we're working with the best information from the right people to make sure this works the first time we install it. And so we'll cover we're not going to dive deeply into installation today, but we'll cover some high-level concepts of what you need to frame your thinking around as we do this. So if you haven't noticed yet, we have a really common theme throughout this entire process of communication, which is super important for so many reasons, as well as of course, the idea that you need to install these things correctly, because you're paying a premium for this equipment, or the customer is paying a premium, and they're expecting to see some really great energy savings. And you also need them to operate really reliably, which will only happen if it's installed the way that the manufacturer insists that it should be installed. And the last thing we want to keep in mind that these are not gas water heaters, so some best practices that apply really well to gas water heaters should be considered carefully when you're installing a heat pump system. So in terms of communication around installation, I talked about how the controls in the design process kind of tied everything together, and all the trades should be tied together in the same way. So that applies really directly to installation as well. You want to make sure that all the trades are talking and that you walk through the installation process with the trades beforehand to make sure everyone's on the same page of what is expected out of this system. And any questions that aren't answered straight through the manufacturer's documentation or through the webinars or any communication you've had up to this point regarding installation should be asked at this point. Lastly, you want to make sure that the rep or the manufacturer are aware of your installation timeline, so they can make sure someone's available on D-Day when this stuff's going in and some questions will inevitably come up. So installation is super essential because you want this system to work as efficiently as possible and reliably as possible. And these are really smart systems, but they need to be applied correctly. And assumptions need not to be made on the controls and things like that, because there's a lot going on in the background a lot of times with these units that are not super straightforward. So it's really important to get all of these installation guidelines down and educate your installation team, because maybe the person or the engineer at the installer's company is really well in tune with these heat pumps, but if the person that's installing your tanks hasn't heard anything about them, then they will put things in that may totally deviate from your understanding and what you've communicated so far. So it's good to get everyone on the team on the same page and answer any questions that come up from anyone on your team. And if no one on the team has an answer or a confident answer, then refer to those to the manufacturer and get those figured out. And I mentioned that these are not gas water heaters. So there are a lot of really great best practices that plumbers have found over the years that a lot of times aren't incorporated into the design drawings, because a lot of times as the designers make these drawings, they don't have the installation expertise that the plumbers do to know of some certain things that become best practice after so many projects are done. But there's some best practices that don't apply to heat pump water heaters, so you need to think carefully about and coordinate with your engineer about those best practices if they deviate from the drawings. One I've seen really consistently as I start up heat pump water heaters is the addition of these check valves in the makeup line to the tanks, which usually works really well, but in some heat pump water heater designs, the heat pump will actually pull cold water out of the tank through the same line that cold makeup water enters the tank. So if through a best practice, the plumber threw in this check valve, now the heat pump can't pull that cold water out of the tank, and so it won't see flow when it tries to run, and then it will go off on high pressure. So that's one example of a best practice that works really well and a lot of times isn't in the drawings, but is added after the fact, that should be talked about with the engineer or the rep before it's applied if it deviates from the drawings at all. And then I'll take a pause here to see if anyone can share any takeaways from the installation, whether it's from personal experience on installations or what you've learned today. And I know our Slido is not super active today, so feel free to drop it in the chat if that's easier than a Slido as well.
So we have a question. I noticed the gas boiler in series with the heat pump water heaters. How do you size this unit?
Gas boiler in series with the heat pump water heaters. So I will, let's see, can I go previously? Yeah, so let's see. I'm not totally sure what that's referring to. We have a heat pump water heater in this picture and some storage tanks. I'm not totally sure which picture they're referring to, so I'm not totally sure how to answer.
They had a follow-up that it was a schematic for Jackson.
Oh,
and set
okay.
that.
Yeah, so we have, at Jackson, we have an electric water heater in parallel with the heat pump water heaters. If you're using a gas water heater, it could be the same way. Oftentimes, I've seen gas water heaters paired with the swing tank, since the swing tank is the last tank that all of this hot water goes through before it serves the building. So the gas water heater can just be paired with that swing tank, or you can use an existing gas water heating system to serve as that swing tank. That would then provide, it would provide the swing tank heating when the primary storage isn't sufficiently charging that tank, and it would provide redundant backup in case the heat pumps go down for any reason. So that's where I've seen boilers work there. Usually not in series directly with the heat pump water heaters, but I've seen instantaneous boilers in parallel as well, as long as the controls are coordinated well and they're not fighting each other to fill those tanks. Because boilers are usually a lot higher BTUs. So if you have the heat pump fighting the boiler to charge the tank, usually the boiler is going to win, and most of the energy being used to heat that water is going to come from the boiler. Yeah, I hope that answered part of the question. Definitely send me follow-ups, and if we get to the end here, we can refer back to that schematic and I can walk through it a little bit more closely. So those are the high-level things to think about in terms of installation. So after we've installed all this equipment, now is the moment of truth in the equipment startup. So hopefully this is a really exciting day for you, and you get to see some heat pumps run and heat hot water flawlessly after all the work you've put into coordinating all of these different steps. So when it comes to heat pump startup, there are a few hurdles, and a lot of these can be mitigated through our common theme of communication and coordination between all the trades. So your trades that are involved in this can be high voltage electric, low voltage for controls, HVAC, because like in Jackson, we're connecting the exhaust of these heat pumps to ducting, and then the plumbing, because the overall system is a domestic hot water system. So if small changes need to be made, you need to make sure that's aware throughout the entire team, so effects from those changes don't ripple down. And you also need to keep in mind that controls, all of these, especially controls, but all of these things usually need to be totally complete before manufacturer's tech can come out and start up the equipment. It's really good to be able to test the entire system as it functions, rather than forcing a heat pump to turn on and have it heat water, but not actually have it respond to the tanks being cold as part of the control sequence. And then I'll do a quick question slide here, but I might not take as long here because you can definitely drop it in the chat and we can stop and talk about any questions as we go through here. Okay, so we'll recap what we've talked about today. And so that started with the overall thing we talked about today was how to get an engineer's design from that design drawing phase all the way up to the operation or the successful operation of the equipment. So we talked about the attributes you want to look out for in the contractors that are installing these systems, and that's proper communication and a willingness to learn about these new systems and a flexibility to make some of these small changes that will come up in these rapidly evolving technologies. And then we talked about how to detail your equipment and the little factors that will change how a heat pump operates in the scope of the entire system, and what you need to make sure you lay out per a specific manufacturer in coordination with their reps and their documents to make sure you have all the kind of have all the boxes checked as part of your design. And then we talked about the verification and purchase of this equipment and all the final checks you should do to make sure that all the information is still up to date and legitimate, as well as lay out all the additional package requirements or extra features that need to come with your equipment as before you purchase it. Then the last thing we talked about was the really high level things you need to keep in the back of your mind as you go through the installation and startup of this equipment. And hopefully this last part is relatively easy if you've gone through all the due diligence through the detailing and the controls and the coordination of your overall heat pump water heater system design. And hopefully the questions I've answered today are, how do I choose the right equipment, and what steps do I need to take to implement a commercial heat pump water heater system? So if there's anything that I've totally glazed over in these and that you'd either like to provide feedback on or you'd like to ask further questions on, definitely drop that in the chat, and we'll also be able to dive a lot deeper into the installation and startup as we cover session 4 next week and talk about installation, startup, and the maintenance of these systems after they're already running. So that last session I mentioned is through the Lighting Design Lab at Seattle City Light, and it's labeled the Design, Maintenance, and Operation at session 4 on February 15th from 10 to noon. So that'll be next Tuesday at the same time from 10 to noon. And that's all I have today scheduled. We have about 15 minutes. If anyone has any additional questions or anything like that, we could definitely address those now. This is where, if you want, we can get totally off topic in the last 15 minutes talking about heat pumps. But I'll stay on the line here in case anyone has any additional questions. And maybe I can use this time as potential questions pop up to go back to the piping schematic and walk through that in a little bit more detail to address that question before. We'll see how quickly you can review a presentation in reverse as we do this. No, we're almost there. Right, so this is I believe this is the schematic I was asked about, and in terms of how you might incorporate a boiler, I'll start with a little bit more in-depth flow logic here, and that is, so the cold water supply is flowing into this primary storage. It's not flowing into this temperature maintenance tank at all, because this temperature maintenance tank is only satisfying this closed loop here. So we want to make sure the water in those pipes are always warm. So we're constantly circulating it and replacing with fresh hot water, and then reheating that warm return water with the dedicated heater. So in this case, it's a heat pump water heater, because that's the most efficient way we found to heat it with this building with a larger loop, and a dedicated tank. But this could be an electric heater, or it could even be a gas boiler if you have an existing boiler system. But when the building actually needs hot water, and that's going to leave this closed circulation loop and go out the tap, that's when hot water needs to be supplied from this primary hot water system. So it's coming from this hot storage tank and going out to the loop and then leaving a tap. And this storage tank is maintained through these primary heat pump water heaters. So their job is to keep this totally charged. And then as really high peak loads come through, all this extra storage is going to be used to satisfy those peak loads, like when everyone takes a shower or anything like that. So incorporating back up here, what we don't have pictured from our system at Jackson, just so we could show a simplified heat pump view, is we have a redundant electric resistance heater that is sitting in parallel with these primary heat pump water heaters. So it pulls this cold water out of the bottom of the tank just like the heat pumps would, and then it heats it up to 140 and then dumps it into the top of the tank. So we maintain that stratified storage, but now we have backup in case these heat pumps either fall behind or they go down for any reason, for maintenance or any other reason. And then we have the controls that ties into, it reads the temperature through these tanks, and it tells these heat pumps when to run based off these separate tank temperatures.
Evan, so we did get a question from Darren. What would happen if you pipe the primary heat water storage tank to bottom of temperature maintenance tank instead of to discharge?
Yeah, so if you move that to the bottom of the temperature maintenance tank, now we have a swing tank system, right? Or temperature maintenance in series is another way to call it. So what's happening there is, let's pretend there's no usage at all, no hot water usage here in the middle of the night. We still have this closed loop through the temperature maintenance tank. And since there's no hot water usage, we don't have any water flowing from this primary storage tank. So you need some sort of heater in this temperature maintenance tank to make up that heat that's being lost in this closed loop. As soon as there's usage from the building, then we have that hot water flowing from the primary storage and into the bottom of this temperature maintenance tank, flowing through the temperature maintenance tank and then out to the fixture. So now that hot water that in some of these systems is 150 degrees is actually heating this temperature maintenance tank as it works its way through and goes out to the fixtures. So that's the big difference there, is in this system, when there's water being used by the building, this primary storage is not interfacing with this temperature maintenance tank to actively heat it up. This temperature maintenance tank has to consistently be heated by this auxiliary heater, whether there's usage or not. In a series storage, this auxiliary heater does not need to be used if there's enough hot water usage that pulls this primary storage through the temperature maintenance tank and effectively heats it before it's being used by the building. Yeah, so oftentimes in a swing tank, since that auxiliary heater doesn't need to be used as much, that's when we'll see an electric resistance heater or just a simple electric resistance element in this tank, because it's not using a ton of energy. First off, it's just the recirc load, or the temperature maintenance load, as we call it. And it doesn't even need to satisfy the temperature maintenance load when there's usage and it's being heated by this primary storage. No, that's kind of a lot to take in. If you didn't follow that, it's totally understandable. And Colin has a lot of presentations with DNR that go and compare those two systems specifically. So it's really great content to look into. And Sarah, Sean, were there any additional questions or anything, or should we go ahead and close this out?
That looked like all the questions for right now, at least. So it's your call.
Yeah, I think we might be able to give about 10 minutes back to people throughout their day. So, say you're in a presentation and take a long lunch or get some extra work done. But I really appreciate you guys hanging out with me and hopefully getting some valuable information here. And I hope to see you in next week's session as well. And I appreciate Sarah and Sean from DNR backing me up here, and the Lighting Design Lab hosting us. to get this information out there.
Thank you, Evan.
Thanks, Evan. Thanks, everyone.
All right, thanks everyone. Enjoy the rest of your week.